Okay, thank you for viewing my talk today on demand. I'll be talking about the impact of Northern Hemisphere mid-latitude anthropogenic sulfur dioxide emissions on local and remote tropospheric oxidants. I'm Dan Westervelt. I'd like to acknowledge my co-authors, Arlene Fiore, Colleen Boblitz, and Gus Correa. Emissions of aerosols and their precursors have been decreasing substantially in recent decades. On the far left here is a plot of global SO2 and black carbon emissions historically and into the future projections. And you can see that there's been big decreases over the last few decades, starting in about 1980, that are projected to continue. We also see this in satellite retrievals of SO2 emissions. For example, in the plot on the far right, we can see in the red line, China's SO2 emissions are in decline in recent years and are expected to continue that way. This is not the case for some places such as India, which is shown in the blue there. You have an increase in SO2. So there are going to be big changes coming, and there already have been some changes coming in aerosols and emissions of aerosols and their precursors. And it seems to be kind of a regionally dependent thing. So what we want to focus on in this work is what is the impact of these regional aerosol emission changes, which are mostly decreases, on tropospheric oxidation, and particularly looking at concentrations of common oxidants and radicals and other trace gases, things like OH, HO2, NO2, ozone, and some others. We also want to look at what's the dominant mechanism for this aerosol impact on tropospheric oxidants. Is it the heterogeneous uptake, which is aerosols serving as a surface for chemical reactions that can occur where things like the HO2 radical is removed from the atmosphere and incorporated into an aerosol surface? Or is it through photolysis modulation? And so aerosols also scatter or absorb incoming solar radiation, which can play a role in affecting photolysis rates, which then can affect oxidation in the atmosphere. So we want to look at that, and also how the impact of aerosols on oxidants vary regionally, especially given the different regional emissions that are occurring right now around the world. Previous work has suggested that the presence of aerosols globally, all aerosols, both natural and anthropogenic, can reduce global mean OH by about 9%. And this plot here in the bottom is showing that for some geoschem simulations that were done quite a while ago now, showing the change in OH from a simulation that has the aerosols active versus one that doesn't have any aerosols. So prior work like this is mostly considered global aerosol perturbations, and has focused on things like dust and sea salt rather than the anthropogenic aerosols. So in this talk, we're going to focus mostly on regional emission changes and focus just on SO2 and its the precursor to sulfate aerosol. So I mentioned that there's thought to be two main pathways between the effects of aerosols on oxidants and trace gases in the atmosphere. And one of those is heterogeneous uptake, the other is photolysis. And so I just wanted to give a quick overview of the way that those are treated in this study. And so in this study, we're going to be using the Geophysical Fluid Dynamics Lab Atmospheric Model 3, GFDL AM3. And so there's an expression below there for the rate constant for uptake by aqueous aerosol. Without getting too much into the detail, the key parameter to focus on is the gamma in this denominator of the second term here, which is representing the reactive uptake coefficient or the reaction probability. And on the right in this table, I have the reaction probabilities, the gammas, listed by the different heterogeneous uptake reactions. So for HO2, we have a gamma of about 0.2. Previously, it had been set a little bit higher, but we think that 0.2 is consistent with a lot of recent laboratory and field studies. The other gammas are listed there for the other reactions for N2O5, NO3, and NO2, which also can be taken up by aerosols. The higher the reaction probability or reactive uptake coefficient, the faster the reactive uptake occurs. We also consider the photolysis effects of aerosols in an online manner, and so the FAST-JX module has been incorporated into the GFDL AM3 model to calculate the impact of online aerosols and clouds on photolysis rates. So our simulation setup to analyze this question is to use nudged GFDL AM3 simulations for the year 2015, nudged to NCEP reanalysis. And we have a control simulation in which we use the standard RCP 8.5 2015 emissions. Then we conduct a series of perturbation simulations in which the emissions of individual aerosol species where their precursors are set to zero over a particular world region. We're going to focus only on SO2 here. So this will be, for example, setting the SO2 emissions over Europe equal to 0 and comparing that to the control. So if we take the difference between the control minus the perturbation, we get the response of anything really, but we're going to look at tropospheric oxidants to aerosols. And so here's a list of some of the things we've looked at so far. We look at three main regions here to assess the change of SO2 emissions on tropospheric oxidants. And so one is the US, where we zero out the US SO2 and compare it to the 2015 RCP 8.5. The other is China, and then the other is Europe. And so each of those have a slightly different total perturbation, where the US SO2 perturbation is the smallest and the China one is the largest. This plot is showing the relative or percent impact of SO2 emissions on sulfate concentration, sulfate aerosol. So you'd expect that as you remove this SO2 emissions, the main source of sulfate aerosol, you would also remove sulfate. We're actually doing the difference the other way here. So this is representing sort of the inclusion of the SO2. And we're going to show mostly results for the springtime, March, April, May, which has the largest impacts in oxidation and in changes in sulfate. So the first row is for the US, the second row is for Europe, and the third row is for China. And we have the surface on the right column and the zonal plots on the left. You can see that the biggest changes are, of course, locally at the surface, but we do get large changes, up to about 40-50% in the upper troposphere and also into remote regions from where the SO2 is emitted. And so this includes places such as the Arctic. You can see that there's significant changes in sulfate in the Arctic and in the upper troposphere. What does this do to HO2 and OH? So as you could expect, it's largely a decrease of up to about 10% globally. Sorry, not globally, 10% maximum in a certain region. So sulfate surfaces directly uptake HO2 radicals. And that's how we get the decreases here on the right column, which is showing the HO2. The left column is showing the OH, which also decreases via the rapid cycling between HO2 and OH. We found the largest perturbations again to be in the springtime, which is what we're showing here. And we see that there's a large relative decrease in the middle and upper troposphere and in the Arctic compared to the surface. So the effects can be very important remotely and not necessarily locally to the emission source. And these also can be regions that don't necessarily have a lot of OH to begin with. But there's widespread statistical significance throughout most of the northern hemisphere troposphere. The changes in NOx respond differently to the inclusion of the sulfate aerosols. So we have a relative increase of up to about 7% in springtime NOx, mostly in the northern hemisphere. So the first row is showing the US, the second row is showing Europe, and the third row is showing the response to the China sulfate. So it's an increase everywhere. It's the strongest in China, which is the case for most perturbation, or is the case for most species that we look at here, just due to there being more sulfate being perturbed. Sulfate aerosols can directly take up NO2, but that's with a very low reaction probability. So that's why you're not really seeing much decreases here. Instead, what we're getting probably is a reduction in the sinks of NOx via OH reduction. So OH is strongly decreased, as we saw, and then that slows down the sink of NO2 plus OH to nitric acid, thereby increasing NOx. And then also there can be reductions in the sinks, for example, nighttime sinks, N2O5 and NO3, which are taken up by aerosols. And so those slowing down of those sinks can increase NOx. But despite the NOx increases, the springtime ozone increases by up to about 4% in the northern hemisphere. So there's changes everywhere, which mostly the increases in things in the southern hemisphere and in the upper troposphere are largely statistically insignificant. So only these decreases are significant. So we see increases of a few percent with statistical significance in each of the different perturbations in ozone. So we want to know, okay, what's going on here? And what's happening is that both production of ozone and loss of ozone decline, but the production of ozone decreases more strongly than the loss of ozone, which lowers the ozone concentrations in the presence of sulfate aerosol. So on the left column, I'm showing the production rate of ozone, defined as you can see here on the right. The left column is showing the loss of ozone, defined as in the text. And of course, the different rows are the US SO2 perturbation, the Europe SO2 perturbation, and the China SO2 perturbation. And so you can see that the production of ozone decreases more strongly than the loss of ozone. And so the decline in HOX and its impact on production of O3 outweighs the aerosol-induced increase in NOx, which would lead to increases in ozone. So it's kind of like the decline in HOX, and therefore the decline in the production of ozone wins out over the decline in the loss of ozone. We also looked at the photolysis rates and how aerosols can impact photolysis rates. So this is showing the difference in JO3 to O1D on the left and JNO2 to NO on the right, just for the perturbation of Chinese SO2 emissions. So you can see there is a small decrease in the photolysis rates in the presence of these sulfate aerosols, but it's mostly locally over China, and it is only statistically significant over China. It's also a bit smaller than relatively smaller than the changes that we saw due to heterogeneous uptake. So we also saw that sulfate aerosols have a smaller impact on photolysis rates than absorbing aerosols. So when we look at black carbon, we get a bigger effect. But we can conclude, at least for SO2, that photolysis rates are a smaller contributor to the aerosol-induced impact on oxidants. So the summary is that reactive uptake dominates the aerosol impact on remote oxidation. So it dominates over impacts on photolysis. Northern Hemisphere SO2 emissions can change OH by up to 10%, even in remote areas. So places like the Arctic, the middle and free troposphere, the upper troposphere. Ozone changes are more sensitive to HOX decreases than NOx increases. So even though NOx increases, the HOX decrease, which slows the production of O3, decreases more strongly and increases the ozone. And then finally, as an application to air quality, the surface ozone decreases by up to 5 parts per billion for 2015 SO2 emissions. So aerosol removal could have the unintended consequence of increasing surface ozone and thereby offset or mask surface ozone gains achieved by regulation of other pollutants. So the plot on the far right here is showing that, where you have the changes in MDA8 ozone from the US, Europe, and China from those sulfate aerosol perturbations, you can see you get decreases in ozone. So with that, I'll stop and look forward to the live session. Thanks.